Okay, so thank you. So my talk is based on, I thank the organizers for the invitation. And my talk is based on the collaboration with Matsuike and Yoneyama. So I try to finish in about 35 or 40 minutes so as to secure your coffee time. Yeah, so the content is as follows. So first I explain what I mean by quantized six-vertex and the Yang-Baxter equation, and then I present the solution. And then I explain the relation to the representation theory, named the quantized coordinate link. But this section 3 is kind of side remark. And section 4, I present the conjectures on the tetrahedron equation of type RRRR. So what is quantized six-vertex model or Yang-Baxter equation? So everybody knows the Yang-Baxter equation. By the way, can you see the cursor, my cursor? So everybody knows the Yang-Baxter equation. And quantized Yang-Baxter equation, I introduce one more extra space on which these L operators act, which is shown in red letters, and relax this equality to the equality up to conjugation. This conjugation is represented by R, new object R here. So it's a Yang-Baxter equation up to conjugation. And it's also called RLLL relation. So it is a version of the tetrahedron equations, originally going back to Sasha Zamorozhkov of 1980. So it has appeared in several guises and has been studied from various viewpoints by many people listed here. And some of the work is quite recent. So just to remark, it has some intriguing application to the stationary states in multi-species TASEP and TASOP in 1D. But I don't have time to talk about that. So I introduced one more space denoted by 3. So I call it auxiliary space. As for the first two spaces, I assume that it's act on its C2 tensor C2. So it's really six-vertex-like, but its Boltzmann weight no longer scalar, but it takes the values in q-Weyl algebra WQ or q-oscillator algebra OQ. Actually, I'm considering specific representation of these algebras, and depending on the choice of the representation, I have 3 L's. So for the q-Weyl algebra, I have 2 representations, and corresponding to those choices, I have 2 kinds of L operators. And for q-oscillator case, I have LO. So we will consider the 3 kinds of L operators in total. I'm going to explain what's those q-Weyl algebra and q-oscillator algebra. First, q-Weyl algebra. So it's very simple thing. So generators are x, z, and their inverses, and with only relation like this. So q, I assume that q is generic throughout my talk. So it has very natural representations. So pi x, one of the representation, pi x is a representation where x becomes diagonal. Pi z, where z becomes diagonal. So these are very simple things. And these are irreducible representation on the Fock space, where index m runs from -infinity to +infinity. So as you see that this commutation relation is a Q analog of the canonical commutation relations of coordinate momentum. So pi x and pi z are equally kind of justified representation. They are coordinates or momentum representation of the Q canonical commutation relations. These are Weyl algebra, and they are 2 representations that I'm concerned with. Now I go to the q-oscillator algebra. So this is also the simple thing. So the generators are k and a plus and a minus. So they satisfy natural oscillator type relations, namely a plus is creation, a minus is annihilation, and k is diagonal, counting the number of bosons or oscillators, making the q countings of bosons. So the most typical representation is pi O, where k becomes diagonal like this, and a plus acts as a creation, and a minus as annihilation. But this is oscillator, so some typical coefficient or factor typical to the characteristic to the oscillator case. So since this factor is vanishing at m equals 0, so I can consider the irreducible representation with m running from 0 to +infinity rather than -infinity to +infinity as we had in the previous page, like this. So somehow pi O is kind of smaller, and the Fock space of the non-negative parts I denote by F plus. So as you may guess from these simple representations, so there is an algebra embedding algebra homomorphism, sending q-oscillator algebra to q-Weyl algebra in this manner. So if you assume the Q commutation relation for X and Z, these relations are easily recovered. So somehow OQ case is a kind of a sub of WQ, and WQ is kind of more general, but this kind of contraction or a kind of smaller Fock space leads to somewhat interesting results. Those are the q-Weyl algebras and q-oscillator algebras. And now I define the quantized six-vertex model. So as I said, I have LX, LZ, LO, and they are defined by a quantized six-vertex weights. So namely the six-vertex model with whose Boltzmann weights range over those representation theoretical things. So I denote, as usual, the six-vertex weights by this sort of vertex configuration. And I have the six-vertex conservation law of a weight conservation along southwest to northeast. So number of 0 and 1 are conserved in this direction, like six-vertex model. And LX is defined by these q-Weyl algebra elements with this representation, so namely pi x representation. And similarly, LZ is defined by these Boltzmann weights, but X and Z are represented by pi Z representation. So Z becomes diagonal for LZ, and LX contains diagonal X, and LO similar. And here, so R, S, T, W are the parameters entering in this q-Weyl algebra case. And for q-oscillator case, there is a single parameter, which I denoted by mu. So these are the three L operators, which may be regarded as quantized six-vertex model. So if you know the six-vertex model well, so there is a special point of the parameter where it becomes free fermion-like. So that condition is called free fermion condition. And roughly it may be, so let me remind you the free fermion condition. You take the product of first two, plus you take the middle two, is equal to the product of last two. That's basically the free fermion condition, free fermion point of the six-vertex model. So that means, for example, in this case, 1 minus q times k squared is equal to a plus a minus. And it's like this. And similarly for this q-Weyl algebra case. So somehow this six-vertex model is free fermion-like, but of course it's a kind of quantization. So I've explained the L operator acting on the three vector spaces. One is this line, and another is this line. And the last line is kind of perpendicular to the seat and on which these operators act. And these are F or F plus, that's infinite dimensional Fock space. So as a short summary so far, by quantized Yang-Baxter equation, I mean the RLLL relation, and it is a version of the tetrahedron equation written in this manner. And if I denote the quantized WQ valued or OQ valued Boltzmann weights in this diagram, it's represented by this. Or graphically, you can draw like this. So as usual, you have the Yang-Baxter sum with respect to these internal lines, alpha, beta, and gamma. And I, J, K, A, B, C are outer lines, which takes a value from values in 0 or 1. But actually, there's those q-oscillator or q-Weyl algebra act on perpendicular on these red points, and R's kind of do the conjugation, achieve the conjugation equivalence. That's a RLL relation, a quantized Yang-Baxter equation. So our attitude is, I already specified L operator very concretely. So this is the equation on R, which is linear. As I said many times, so I consider three kinds of L's. So this L can be chosen LX, this can be chosen LZ, and so on. So depending on such choices, I have many variety of R's like this. So in general, if I have LA, LB, LC, where ABC runs from X, Z, O. So the resulting R, if it's unique, it will be denoted by RABC. And so I'll call it R or 3DR. So this is an example of the RLL relation for q-Weyl algebra case. So I substituted this to this object, the expression coming from this. And I have denoted this combination by Y. And because we have 3 components, there are parameters depending on the indices like this. So as I said, those ABC, IJK, depending on these choice of IJK, ABC, 0 or 1. So there are number of equations. But because of this 6-vertex model conservation rule, there are not so many. So actually there are many, but not too many to analyze. So I suppose there were 18 non-trivial cases. So the main result. So there always exists a unique R up to normalization in each sector specified by an appropriate parity condition. I'm not going to explain this parity condition in detail. So it's a bit technical thing. So you may not, you can, please do not care so much. So actually, this is a summary of the future of the obtained R. So to explain this table, let's come to this formula. So action of R can be described in this manner, where IJK runs from minus to infinity to plus infinity for Weyl group case, a Weyl algebra case, and q-oscillator case, they runs from 0 to infinity. So its action in general can be described by the action on the base vectors of the tensor cube of the Fock space. And this R, ABC, IJK is a matrix element. So in general, it is going to be the function of the Q and various parameters that I've already introduced. So this is a matrix element. So we say that R is locally finite if this quotient is 0 for all but finitely many ABC for any given IJK. That is, so if I pick up one base vector, and if this summation is going to be infinite sum, that's not locally finite. So this locally finite means this is always finite sum for any choice of IJK. That's a local finiteness. So now let's come to this table. So we have not completely existed the general choices, but for O and Z type, we have done that. And the future is, it says factorized or 251. By the way, 251 is a q-hypergeometric. So by factorized, I mean that this matrix element is factorized in some sense. Yeah, completely factorized. So it's either factorized or q-hypergeometric like, except this 3/2 like thing, but this is a bit technical. And locally finiteness, so we have some cases yes, some cases no. So these are the summary of the future of the solution that I've got. So these are new, except this OOO case. I'll show you the explicit, some of them explicit form, in a minute. And this is the first result. And the second result is, as I already mentioned, there is one proposition stating the relation to the quantized coordinate ring of type A, AQSLM. And the last result, or maybe conjecture, is parity of this kind of tetrahedron equation. So first, let me present some of the typical solutions from this table. So the most typical case is this ZZZ case. So, OO case was known. So somehow ZZZ is kind of most extremely typical new result in this talk. So it's like this. So by the definition, it acts on the tensor cube of F. And as I explained, so this representation carries a parameter RSTW, but we have 3 components. So we have these 12 parameters. And this matrix element is given by this formula, where D1, D2, D3, 4 is given by this formula, given those 6 indices, and phi as well. And this capital phi function is by this. By the way, maybe I should have emphasized somewhat this notation. So this standard notation I will use either for positive or negative n. This is a bit important. So due to, using this definition of infinite, so this definition I use either positive or negative, which is rather standard. So this m can be either positive or negative, and this is the solution. So it's not, it's factorized in the sense that it only contains the product of these things, but it's not locally finite. So this is a typical one solution. Now I changed one of the space from Z to O. So now the first component acts on the F plus, which only contains the parameter mu. And the other space is the same as before. So it contains 8 parameters. And this is a result. So some parameter to some integer power and q factorials and q power of q times q hypergeometric. But this q hypergeometric is actually terminating because of this factor. You see that this I refers to the first component, so that I is non-negative integer. So this is I's order kind of truncation. So actually, this is a rational function. So it's not factorized, but somehow good in the sense that it's expressed in terms of q hypergeometric. But again, it's not locally finite. So this is the future for ROZZ. Next, I further change one of the space into the q-oscillator type. And so let's the parameter corresponding to this mu1 and mu2, so on. So it turns out that there exists a unique solution to the quantized M-Baxter equation if and only if the ratio of these q's are equal to the q to the some power, and this power must be lie in integer. So that may remind you of the some similarity of the quantum R matrix and that sort of things. And yeah, it's kind of yeah. So similarity. And the formula is like this. So in this case, so using this D, I define E and F by this formula. And if this is not the integer, then this R is 0. So assuming that these E and F are integers, then it's given by this form. So this is obviously factorized. So only you have this factor. And moreover, so this E minus A, or that's all factors F, can be either positive or negative. And due to the definition of this q factorial with negative index, so if you closely inspect these ratios, you see that this is locally finite. So there are only finite interval of the ABC given ijk, so that this does not vanish. So it's locally finite and factorized. So this is the last case, which was the known result actually, was all the q-oscillator case. So I attach these 3 parameters and formula is like this. So again, this is not factorized, but again, the terminating q hypergeometric 251. So for this solution, some quantum representation theoretical background is known. So that's the next topic or kind of remark. So let's AQSL3 be the Hopf algebra. So, consider the AQSL3. That's a Hopf algebra dual to UQSL3 and generated by Tij, satisfying this relation. So it's also called a quantized algebra functions. So there are 2 algebra homomorphisms to the q-Weyl algebra by this formula. So this you can elementary check. So row 1 sends this algebra Tij, so 9 generators into this q-Weyl algebras in this manner, where U1, G1, H1 are parameters. And I denote this by row 1. And similarly, there is a row 2. So you see that this is kind of attached to the first node of the linking diagram. This you see kind of SL2 structure, and this is trivial. Here you see that the SL2 structure is on the second node of the linking diagram. Here you see some trivial fact. So row 1, row 2 really correspond to the 2 nodes of the linking diagram of the SL3. So there are 2 such well-known representation or homomorphism. And if I further take this parameter especially like this, so then, for example, you see this factor becomes 1 minus x squared times z inverse. That's a combination that we encountered. So actually, it's not going to the full of q-Weyl algebra, but it can stay within the q-oscillator algebra. So for this special choice of the parameters, the image can be regarded as a q. So that's a story about this upstairs. So from the quantized algebra functions with specialized parameters, that row 1, row 2 sends the generators into the q-oscillators, and you can evaluate these q-oscillator generators by representation pi o, and then you obtain the map, linear map on this Fock space. So let me denote this representation of this AQ by rho OI, where I is 1 or 2. Then what is known about, now I can explain the known facts about ROOO. So Soibelman proves that the tensor product of this form and this form are isomorphic. So as I said, this AQ is Hopf algebra. You can consider the tensor product representation. And you see that this is analogous to the Coxeter relation of the SL3. So the simple reflection S1, S2, S1 is equal to S2, S1, S2. So Soibelman established some general statement that corresponding to such sort of Coxeter relations, you have the equivalence of the such type of the representation, q-oscillator representation of the quantized co-derivative. That's a general result due to Soibelman in the early 90s. Now, a few years later, Kaplanov-Voevodsky actually considered the complete intertwiner, achieving the equivalence of these two representations. Namely, they consider the representation acting on the tensor product of the representation of these spaces in this map. And they obtained explicit formula for this intertwiner phi. Now, very different line of the stream, Vajanov and Sergeyev, 2006, and later with Mangazev, sorry, this is typo, 2010. So 0 and 1 should be swapped. So they consider the RLL quantized Yang-Baxter equation in the very same manner that I'm talking for particular case of all O case, and they go obtain the solution 3D ROO. Now, 2012, with Masato Okado and I was investigating the BC analog of these stories. And as a byproduct for type A, we discovered that this Kaplanov-Voevodsky phi and Vajanov-Sergeyev-Mangazev are the same modulo this simple transposition of the components. So that means this representation theoretical isomorphism has a natural presentation in terms of the quantized Yang-Baxter equation. So quantized Yang-Baxter equation have some good representation theoretical background. That's a story about O. And so what about this Z? See, so I keep these parameters here generic. And so the image stays within q-Weyl algebras for both rho 1 and rho 2. So I send this A by rho, by this map, and further evaluated by this representation pi z. Pi z is very simple. So z becomes diagonal. That's pi z. There is a representation of this Hopf algebra, which I denote by rho zi. So is there any story parallel to these things? And that's this proposition more or less answers it affirmatively. So I consider the equivalence relation or a kind of relation for phi tilde achieving this equality. And remember that this rho zi, rho z2 contains a parameter, triple parameter like this. On the other hand, quantized Yang-Baxter equation for ZZZ type, I have parameters like this. So here I have 12 parameters, and here I have 6 parameters. So actually the statement is these relations are the equivalent in the sense that this achieves the equivalence, provided that the following relation among the parameters are. So that's a proposition. So I think application of this proposition is yet to be explored, but at this moment, so it's quite nice to have that. We also have similar such. We may have such a story for this kind of newly considered representation of this AQ. Anyway, it was kind of a remark. So let me come to the last section. So that's a conjecture of tetrahedron equation of RRR. So you remember that for the two-dimensional case, you have two kinds of Yang-Baxter equation. One is RRR is equal to RRR. Another one is RLL is equal to LLR. So as you see that, as you know that this RRR type Yang-Baxter equation is a kind of consistency of the RLL relation. So it's consistency of the RLL relation. So RLL relation is a kind of simpler. And similar story holds also for 3 dimension. So, the obvious, my question is, we have got many R, 3D R, like in this table. And the question is if they satisfy the tetrahedron equation among themselves. So for to consider such problem, I consider the I use RLLL relation. So the known strategy is the following. So you consider the six product of the L operators, and you let the left side of this tetrahedron equation act on it. And here you let the right-hand side of the tetrahedron equation act on the same product of L operators. Here you see if you look at this first middle four factors, it exactly matches RLL relation. So you can move R to somewhere here and thereby reverse this product of these three like this. But once R is here, then its index and its indices and those indices are distinct. So this R can be pushed through to the right end. So this kind of procedure can be repeated until you let all the train of this four product of R's go through these L operator, six product L operator, thereby reversing the order of the six product. And exactly the same things is induced by the penetration of these four. So that means if you take the ratio of these left-hand side, right-hand side, it commutes with the six product of L operators. So if this action of six operators, L operators, are irreducible on the tensor six order tensor product of Fock space, then Schur's lemma tells you that it must be scalar operator or constant. And this constant can be fixed by considering the very special matrix element, which should be one. So that is going to be the proof of this tetrahedron equation of RRRR type. So maybe this is kind of a digital proof, but maybe it's easier to see what's happening by this diagram explanation. So here you consider the four arrows. Four arrows correspond to alpha, beta, gamma, delta in these formulas. So you have quantized six-vertex model, little small configurations, and each intersection carries a Fock space, which I denote by 1 to 6. So every time you reverse the triangle, you apply the 3DR of the corresponding indices. For example, this maneuver starts from the shifting this arrow to, and then this triangle gets reversed. So sorry, you shift this arrow to the right. So then you reverse this 4, 5, 6 triangle, and so on, like this. And on the other hand, you can also start by reversing this triangle first, and then you reach. That's the explanation of this. So in terms of the representation theoretical of the quantized coordinate link, this corresponds to the transformation of the longest reduced expression of the longest word of the Weyl group element by successive application of the cubic Coxeter relation. So that's kind of a Solvable story, but this is a kind of integrable system explanation of those procedures. So that's the calculation and the strategy. And but in our case, we have three kinds of L operators. So if I denote these kinds of operators by A, B, C, D, E, F, so then we can play the same game for this product of six product L operators. And the result suggest that we may have this equality. So mixed type tetrahedron equation. So as I said, if all the types are the q-oscillator type, the irreducibility known from the representation theory of the quantized coordinate link, then therefore we must have this equality. And actually this was the way Kaplanov and Voevodsky proved this equation in '94. This was known, but the other case is somewhat subtle because the irreducibility, there is some subtlety about the irreducibility of the product. And also another problem is the convergence problem. As I said, some of the 3DR are not locally finite. So the composition contains the infinite sum and whose convergence is somewhat not. So yeah, so the other cases are yet elusive. And so let's write out this formula, a very tetrahedron equation, very explicitly, and for the transition from this vector to this vector. So both sides act on the 6 for tensor product of the Fock space, And so it brings certain base vectors to some linear combination of some other base vectors. So if you pick up the coefficient of this base vector after acting left-hand side, right-hand side to this monomial, then the result is like this. So it contains 12 outer index lines and 6-fold sum. So we are now considering Fock spaces, but suppose we consider just the minimum two-state model. So each side contains 2 to the 6-fold sum, 2 to the 6 terms, and for 2 to the 12, and the number of equations 2 to 12. So it's kind of immensely more complicated than Yang-Baxter equation. So so back to our case. So even this, some of the 3DRs are not locally finite. So if you closely inspect the composition structure of these multiple sums, there are cases where these sums, both sums are finite sums, given those 12 indices. So that's due to the locally finiteness of the part of the R matrix. Not all of the R matrix has to be locally finite. So we have picked up such cases, and that's given in the next page. So there are 24 cases actually. So these four only contain the locally finite R. And these cases contain only one locally non-finite R matrix. So if you consider the both input vector and output vector, if you fix both, then the intermediate sum is finite. And these cases are somewhat more tricky. So they contain more than one locally not finite R's, but nevertheless, due to the very kind of subtle structure of these compositions, both sides stays as a finite sum. So if things are finite, then we can make the computer check. And we did that. And typically each equation has been checked for about 10,000 choices of those outer lines and so on. And they all seem valid. So that's kind of our conjecture. And as I told this story to the Naomi-san, who is an expert in the q-hypergeometric or even elliptic hypergeometric. So he claimed that these equations should be reducible to a duality of his and Ito's multiple series generalization of the q-hypergeometric. So this should be some interesting problem to consider. So I think I'm almost done. So this is a kind of future problem, list of future problems. So as I explained, so there is a good quantization of the Yang-Baxter equation, which is related to the integrality in three-dimensional system. That I symbolically called quantization, but you can go backwards. So given the solution of the quantized Yang-Baxter equation, so those R and L satisfying RLLL relation and so on, so you can reduce them to generate the infinite family of the quantum R matrix here. So when you do these calculations, you can utilize the third dimension, and depending on the size of the third dimension, you can generate the family of the solution of the quantum R matrix. Such kind of calculation has been done in many examples. So it will be an interesting problem to do such trials for the newly obtained solution of the quantum Yang-Baxter. Another topic is Q root of unity case. So as you may know that for so-called generalized chiral Potts model has some origin to the 3D structure with this Q to the root of unity. So the root of unity case is, deserves the investigation. Actually, this is one of the way to regularize the infinite sum. So if you consider the Q root of unity case, you should restrict the Fock space into the n-state model and that sort of things. So that will be some interesting, problem. And ROO, I say that it's a intertwiner of the solvable modules, but actually there is another characterization as a transition coefficient of the PBW basis of the nilpotent part, positive part of UQ plus. So this is quite good characterization, which has an extension to other type, BC and G2 and all type. So the natural question is, if this RGG, for example, has such quantum group theoretical characterization. That's another interesting problem. And the last one is the obvious things to do. So the story I have presented just for type A. So there is natural analog, the quantized reflection equations, and quantized Jitsu reflection is known in the literature, for example, this. So one should be able to play the similar game and try to see what happens. So actually, so some of those background has been surveyed in this book published quite recently. So I think I'm done. Thank you for your attention.
Thanks very much. Other questions? So I have one very general question. I mean, you've defined these beautiful new solutions and talked about their algebraic connections, but can you just say a bit more generally about their use in defining and solving lattice models?
Lattice model, you said?
Yes. So defining higher dimensional lattice models, which is solvable.
Yeah, at the moment, so if you have the tetrahedron equations, you can construct the commuting layer-to-layer transfer matrices. And this layer-to-layer transfer matrices at least contain two spectral parameters and so on. So that's one thing that you can try to solve. But there are very few examples of such cases in which such analysis was indeed done.
Are there aspects of the algebraic beta-ends that survive that give you a way to solve this systematically?
Well, not much is developed for the beta-ends. So that's another future task, I think, to be done.
Any other questions?
Can you say a few more words about the conjecture of Nomi?
No, well, actually, last week we were both in Kyoto and attending the same conference, and he told this me. So he has some with Ito. He has some multiple series generalization. So maybe have heard about the so-called Lamarckian sum. So that's the sum of some Q series Q factorials from -infinity plus infinity. That's all things. And but that is single sum. But he has the good thing about Lamarckian sum is the result is factorized, and it has got some great history. I don't know, but so he has some generalization of such things for multiple sum, infinite sum with Ito and so on. And those infinite sums, as you may find in the book like Gaspar and Rahman, so there is some duality. Some big sum is equal to another big sum. That sort of duality exists. So according to him, he has the impression that this kind of big sum, for example, it contains infinite sum in some case. So sorry, this is finite case. So he claims that even the case where these sums composition actually contain infinite sum, there may be such Lamarckian sums like machinery may work. And in such cases, so this equality may be reduced to the duality of those sums. Actually, he said used more strong Japanese word. Should be, it must be or something like that. Yeah, that was about 4 or 5 days ago. I'm not sure if by now it's a theorem or not. He was claiming so.
No, okay. Do you have a question, Eric?
Yeah, sorry, it's probably a very trivial question, but for someone who doesn't know about tetrahedron equation like me, it was hard to make contact with the weights of the 6 vertex that you showed in the beginning. So for instance, I mean, is there some, instead of this oscillator or Weyl representations that you put, is there some trivial one-dimensional representation which you could put in which then the weights you would recover in the L operators would be just the usual ones of the 6 vertex model?
Yeah, that's a free fermion 6 vertex model. So if I assume that X and Z are all just numbers and the commutative numbers, I think that's more or less free fermion 6 vertex model.
Okay.
Yeah.
Okay. Yeah. Great. Thank you.
But these are actually Q commuting, or WQ or OQ commutation relations. So that's a quantized free fermion type 6 vertex model. Yeah.
So then maybe the question is, what is the solution of the tetrahedron equation corresponding to that specialization?
Pardon, so I couldn't get your question. So.
Oh, sorry. So then if you specialize to these finite dimensional representations, then the solution of the tetrahedron equation corresponding to that, is that
that
Understood.
I haven't. You mean you're saying that the such specialization of the solution of the tetrahedron equation reduced to what we are familiar in the 2D. That's you're saying?
I'm not sure. I'm asking what it might be. So
Yeah. So maybe that corresponds to the specialization of setting q to the 1. So yeah, q to the 1. So as you may see that q to the 1, yeah, kind of rather difficult. Yeah.
Okay.
Yeah, it's maybe not so direct to see the degeneration to the known cases. 1 is certainly the root of unity case, so it's quite similar.
Uh-huh.
Yeah.
Anybody else? Okay, well, thank you very much again.
Thank you.